Alright guys, welcome to a new session on trigonometry. It's a continuation of the series. Last time we just, if you guys remember, we talked about type 1 compound angles or the sum and difference formula, and it was a two-part series. In part A we discussed the concepts on what is compound angles and what are the sum and different formulas specifically to sine and cosine, and in the part B we spoke about we took some of the examples from the last 4 years of the question papers, and we kind of solved them and see how they relate to the actual problem solving, and we kind of got some security around how to score marks or how to make sure that we solve the compound angles problem properly. And like I said, the whole trigonometry is divided into 7 types of problems, and we completed type 1, and today we're going to talk about type 2, which is something called as allied angles. And like the previous series, I'll make this series into two parts. Part A will be the concepts around allied angles, and part B will be some of the problems from the past question papers we can solve to see whether how to understand, how to apply the things that we learned in part A or the concept, so that we make sure that our understanding is solidified. So with that, let's straight away jump into the part A of this series of allied angles, and let's talk about allied angles. So type 2 allied angles is an interesting concept, and before we jump into what is allied angles, let's do a quick refresher on some of the things that we already know, and possibly some of the things I might introduce in today's session. So with that, the first thing that we are going to talk about before we talk about allied angles are complementary angles, and then I'll introduce you a new concept of co-function identities. So what are complementary angles? So we know that in a triangle there are three angles, right? A, B, C, and all those three angles add up to 180 degrees. We know that in any triangle, we know that. And for by any means, if two of these angles, it could be A, B, A, C, or B, C, if any two angles add up to 90, then they are got complementary, like I have written here. They are called as complementary. And coincidentally, in a right angle triangle, one of the angle is already 90, so the remaining two angles, which is this and this, they ought to be they ought to add up to 90 degrees, and hence they will be complementary. So let me repeat it once again. In the right angle triangle, the angles excluding the right angle will be always complementary, because one is 90 and all of them need to add up to 180. We know that. For example, if you see here, this is a right angle triangle, this is the right angle. So if this angle is 20 degrees, this will be 90 minus 20, which is 70. And if you add up all of this, 70 plus 90 plus 120, it will add up to 180 degrees. Similarly over here, if you see, if this is your right angle, and if I take any angle and assign it the value of 30 degrees, the third angle will be always 90 minus 30 is equal to 60, and hence this angle and this angle are complementary. Over here I have written, so in this case, in a right angle triangle, 60 plus 30, these two angles are complementary because they add up to 90. In this case, the angles 70 and 20 add up to 90, and hence they are called as complementary angles. So that's pretty straightforward, and we know that it was just a refresher. Now moving on, so what is significance of the complementary angles in the context of trigonometry? And the significance is trigonometry functions exhibit a very unique and interesting characteristic when it comes to the complementary angles. Okay, and let's see what those are. So if you see here, I have just did a refresher here, and I've added all the trigonometry functions. This is your right angle triangle, and I've just called out sine, cosine, sine, cosec, cosine, and sec, and tan, and cot, and I've just defined them, which we know and which we have done ample number of times. And I've also taken a right angle triangle just for illustration purpose. And if you see here, this is my right angle, and this is my theta, which is any angle, and this is going to be 90 minus theta, because we know that this angle and this angle are complementary from this example. So this like kind of the guiding principles, the base that I've set up. Now let's see what is the peculiarity over here. So let's take this angle. Okay, let me erase this so that we know what's going on. Okay. All right, one second, guys. So what happened to my eraser? Okay, it's not working. The eraser is not working. Okay, let's move on. So if you see here, this is my theta and this is my 90 minus theta. Okay, so let's say let's take any trigonometric function. For example, let's start with sine. So let's take sine of theta, sine of this function. Okay, sine of this function is going to be over here by definition opposite upon hypotenuse. So over here sine of theta is equal to be opposite, which is AB. We have AB here, and then hypotenuse, which is AC. Okay, so we got that. It's straightforward, no brainer. And let's move on to the complementary angle, which is 90 minus theta. This angle, right? This is 90 minus theta. So let's say for this angle, instead of taking sine, for the complementary angle, instead of taking sine, let's say we take a cosine function or cosine of this angle. So what would be cosine of 90 minus theta? And we know that cosine is adjacent upon hypotenuse. So over here, cosine of this angle, the adjacent angle is AB, okay, and the hypotenuse is AC. So if you see here, cosine of the complementary angle is equal to adjacent upon hypotenuse, which is AB over AC. It's interesting. So looks like for the trigonometry value, sine for an angle has the same value of the cosine for the complementary angle because the ratio of the sides are the same. And that kind of pretty much applies to all the parts. If you take in this case cosine of an angle, so let's say this is, you take this as the cosine, okay, and if you take cosine, we know that cosine is adjacent upon hypotenuse. So adjacent is BC over here, BC, and upon AC, okay. And if you take the complementary angle 90 minus theta, and instead of cos this time let's say sine, let's take sine 90 minus theta. So sine is always going to be opposite upon hypotenuse. So the opposite is BC, which is the same angle as the cos. For the cos it's adjacent side, and the hypotenuse always remains the same, so that's AC. So in this case again we are kind of getting a peculiar feature of the trigonometric functions where the trigonometric function of one angle is equal to a different trigonometric function, and the angle is a complementary angle. For example, cos moves to sine. So in this case sine was moving into cos, in this case cos is moving into sine, and if you go so on and so forth, we'll see that tan moves into cotan, or cotan moves into tan, vice versa. Cosec moves into sec, and sec moves into cosec. And this, which is very evident. I'm not sure if you guys noticed when we learned this table in the very first video, the values repeat. For example, if you take sine here, sine of 30 is equal to cosine of 60, right? 30 plus 60 is 90. So it's the same thing we're doing it here. So in this case it's a table and we can see it spread out linearly. In this case it's an angle, but it's the same thing. Sine of 30 is equal to a cosine of 60. Similarly, cosine of 30 is equal to sine of 60. Same stuff, right? And we can prove it for all the angles. You can see, you can take any angle and you will see. For example, if you take tan of 30 is equal to your cotan of 60, because 30 plus 60 is complementary, so the angles has to be complementary in nature, and that way we can see that there is a specific characteristic it exhibits. And what are those characteristics? The characteristics are sine becomes cosine or cosine becomes sine, and tan becomes cotan and cotan becomes tan, cosec becomes sec and sec becomes cosec. So that gives us the concept of co-functions over here, right? What are the co-functions? Co-functions are nothing but whenever you see these characteristics where the trigonometric function of an angle is equal to the co-function of the angle and the complementary of that angle. For example, over here, trigonometric function of angle A, let's say any angle A, will be equal to trigonometric function of another trigonometric function 2, and it is 90 minus angle A, which is a complementary angle. Whenever you see any two trigonometric functions exhibiting this particular characteristic with one angle and the other being taking the complement of the angle, in that case or in those cases, these two trigonometric functions are called as co-functions. And like I have explained you here, the co-functions are sine becomes cosine, and sec becomes cosec, and tan becomes cotan. And if you remember in the very first video when I was talking about the history of trigonometry and how sine and cosine got the name, you must remember the sine got the name from Gia and cosine got the name from cotigia. So that the coti of the prefix co is kind of getting from there, because in even back those days in ancient years they figured out that sine and cosine are, they do have a complementary relationship when it comes to the two angles which are separated by 90 degrees, and that's reason co. And the easy way to remember the co-functions is just pick up any function, and the other function, for it to be its co-function, it has to have a prefix of co. For example, if you take sine, what is the co-function of sine? You just add co and it becomes cosine. Sec, what is the co-function of sec? You just add cosecant and it becomes, these two become the co-functions. And similarly tan and cotan. So whenever you take any function and add prefix of the word co, right, as a for the co-function or for the exhibiting the complementary nature, those two functions become co-functions. Kind of easy to remember on how it converts. And with that, let's move on. Let's see where we are going with this. Okay,